Hey, hello everyone. Welcome to another Data Science Club session. Today we'll be continuing with our geospatial analysis that we did last time as well. We completed the first exercise where we built our first map. We were looking at some loan data that one of the non-profit organizations had, and we looked at some data relevant to Philippines. Where do they have where do they have the most branches or the people who give out loan, and based on how the data was visualized on the map, we had to figure out what can be the next place where they can branch out in Philippines. And similarly, we saw that you could have actually plotted that data throughout the world, and Philippines was one example we took, but we could have just as easily been like, what's the next place that they should start for branching out in India? It was just a simple single line where we were filtering out just the results for Philippines. So we'll be continuing with our geospatial exercises, and the next one that we'll be doing is coordinate reference system. Um, if you guys haven't done the first video, I strongly encourage, and like most of you already know now, it's always good to go at least start with the first exercises and just go part one, part two, part three, part four, rather than just starting in between, because sometimes we have some knowledge base over here that we'll be using in the next exercises. So go and do the first one and then come back over here for our second exercise. And like always, it's on kaggle.com. Go to courses and there will be a geospatial analysis. That's where you'll find it. And we'll go through the tutorial first, and then we'll come to exercises.
Sounds good. Let's do it.
All right. So coordinate reference system. The maps we create in this course portray the surface of the Earth in 2 dimensions. But as you know, the world is actually a 3-dimensional globe. So we'll be we will be using a method called map projection to render it as a flat surface. Map projections can't be 100% accurate. It distorts the surface of the Earth in some way while retaining some useful property. So there is this equal area projection. So it preserves the actual area of the place. And there is equidistant projection, so preserves distance.
Mm-hmm.
So
Right.
they also have examples on when you should use which one. Um, it was a while back when I read somewhere that I don't know what's the famous cartography map or the map that they had. It was basically like everything in the however north you go from the equator, everything starts becoming larger and larger. So it distorts the actual size of the continents or the actual size of the countries. So um, this looks like the first one looks like it will give you an equal area of the land masses and
Mm-hmm.
equidistant just how far they are.
Yeah, I think the Mercator is infamous for doing that. That's the one that a lot of people see in, magazines and things like that.
Yeah, yeah. I always thought, I mean, Greenland is very big, but I always thought Greenland is way bigger than it is.
And if you ever want to prove to yourself that you can't project a surface of a sphere onto a plane perfectly, try
Yeah.
to unwrap an orange without tearing it. Right? And that's
Yeah.
because that's area preserving and distance preserving if you don't tear it.
Yeah. All right. So we'll use a coordinate reference system to show how the projected paths correspond to real locations on Earth. And so, so setting the CRS. Uh,
Mm-hmm.
oh, so when we import a geodata frame from a shapefile, the CRS is already imported for us.
Yep, our coordinate reference system.
How do you interpret that?
Cool.
European Petroleum Survey Group, so EPSG codes.
Oh, okay. So that's presumably a standard defining body.
Yeah.
DSG, and then they
And it
have a
is
number.
commonly called Mercator projection.
Okay.
And slightly distorts area. Okay. This projection preserves angles, making it useful for sea navigation, and slightly distorts area.
So that's where it's useful. Good to know.
Yeah, yeah. I wasn't sure what was the user and everything of that, but yeah, that's a good reason to have those. Because earlier maps were built for navigating over sea or
Mm.
ocean. All right. However, when creating a geodata frame from a CSV file, we have to set the CRS. So EPSG40 corresponds to coordinates in latitude and longitude. And so if we have a CSV file, we convert it into a data frame, and then we get geometry. So points from XY, and then we specify a longitude and latitude over here. Since it's not a shape file that we are importing a CSV file. And then you have to set your own EPSG.
That makes
So
sense. Because where would you put it in a CSV file?
yeah. So then you can check facilities.head and you will have the geometry. So it looks
Ooh,
like the facilities is going to become a shapefile after this.
very nice.
In the code cell above, to create a geodata frame from a CSV, I needed to use both pandas and geopandas. All right, this is pretty good. So reprojecting. Oh, so this is when you are changing the CRS, and I don't know if you can do it in a shapefile or you have to again go the pandas route or create your own geopandas. With toCRS method. Okay. So yeah, you can just change your CRS directly. You don't have to recreate your shapefile. toCRS is okay, and you can just specify EPSG equal to 32630.
Oh, cool.
Yeah.
So it's has a lot of really smart conversions
Yeah. Yeah.
built in. That's great.
Modifies only the geometry column. All other columns are left as is. That's good.
Right, because latitude and longitude is irrespective of shape. It's
Yeah. Yeah. So in case the APSU code is not available in Jupyter, we can change the CRS with what's known as the project for string of the CRS. For instance, the project for string to convert to latitude or longitude coordinates is as follows. So plus project equal to long plus ellipsis. Oh, so this is what that two um, toCRS is doing. It looks like.
Hmm. And where did that come from?
Yeah, it looks like basically it's just changing it over here.
Yeah,
That's
but where did
interesting.
that come from? I mean, it as far they're telling us what it is, but how
Yeah,
would we know what that means or where to find it?
yeah, yeah. This would be good to know. I think you are projecting longitude, ellipsis.
Yeah, presumably it's an ellipse. And
Uh,
datum, I don't know. It sounds
data.
like something out of CAD.
Yeah, yeah. So if somebody has any ideas of what all these variables mean, and I think William is looking it up right now, but if somebody has idea, please post it in comment sections. Um, it looks like it's just taking in the latitude, longitude, and wherever this was not possible, where we didn't have a CRS that was standard that comes with GeoPandas, then and you still want to use this new CRS, you can specify it using this. What it means, not completely sure.
Hmm.
All right, so attributes of geometric objects. For any arbitrary geodata frame, the type in the geometry column depends on what we are trying to show. For instance, we might use a point for the epicenter of an earthquake, a line string for a street, or a polygon to show county boundaries. That makes sense. All three types of geometric objects have built-in attributes that you can use to quickly analyze the dataset. For instance, you can get the x and y coordinates of a point from the x and y attributes respectively. So you get that x dot head, and you can get the length of a line string from the length attribute. So
Right.
regions.geometry.area. Oh, okay. That's pretty interesting. So if it is a line over here and we just wanted to see how long a road is, then we can just find the length value because it's actually showing a line on a map. If it's a point, uh, then you can find the x-axis and y-axis. And if it's a polygon, you can find the area that it is representing. So like, for instance, we are in Jefferson County and we were plotting all the counties in Alabama. So, and if we had this shapefile and we had a polygon value, so yeah, 25. So yeah, if you have this polygon value, you can just use that dot area variable and you should be able to actually get the area for Jefferson County. All right, so use what you have learned to track bird migration to South America. All right.
Let's do it.
Yeah, this sounds like a good exercise. All right, so we are a bird conservation expert, sure, and want to understand the migration patterns of purple martins. In your research, you discovered that they will typically spend the summer breeding season in the eastern US and then migrate to South America. Uh, it's under the threat of endangerment, so you'd like to take a closer look at the location that these birds are more likely to visit. There are several protected areas in them which operate under special regulations to ensure that species that migrate there have the best opportunity to thrive. And you want to know if they actually go in those protected areas. Recently collected data that tracks the year-round location of 11 different birds. Before you get started, run the code cell below to set everything up. Oh, so if this is the first time somebody is using Kaggle exercises, I hope you have gone to the previous exercises because I repeat this in every Kaggle exercise. This is just setting up your Jupyter notebook or this notebook so that any of the hints, any of the solutions that they provide, or if when they check that you have actually put in the correct values or not, all of those things get set up. It also helps you in importing some of the common libraries that you'll be using throughout this notebook. All right, so we are loading. We are loading the data. There are tag local identifiers. So there should be 11 different birds in this data set.
Indeed, there you go.
Yeah, because this should be unique and there should only be 11 of them.
Mm-hmm.
So where each bird is identified by a unique value in that tag. Each bird has several measurements. Okay, so use the next code cell to create a geodata frame birds. All of the columns from bird DF along with a geometry column that contains point objects with longitude, latitude, locations. Set the CRS of birds to init EPSG4326 and all right, and it was GPD, so GPD dot geodata frame, and we have birds underscore df. And how do we specify geometry? Equal to, so we have two values, so location long and location lat. All right, and we need to specify that they are points.
Oh, are we allowed to do that?
There should be some.
With the dashes, because I think it's going to interpret the dash as a subtraction operator, unless it's in quotes.
Oh, okay.
So I'm not sure if
That
there's
we can
any.
specify this. Okay, so we have pandas, we specify this. Oh, GP do, I did not mention this. So we have
Oh.
points from XY.
Location map. Wait, which one goes first? Is it long or lap? Okay, long then lap. Okay. And I think you have to use quotes because again, it's going to think you're trying to subtract the variable long from all the stuff before it.
Oh, okay.
Yeah.
I think I need one more. Oh.
You see what I'm saying about the? Because here you can do it because it's just a single word with no dashes.
Yeah.
You might be able to get away with underscores. I don't know how it works though. Pandas, I can't remember.
We can specify it like this.
No, it doesn't like that. Okay. Yeah, that's what I ended up doing. I think that's. There we go. I think that'll do it. Oh wait, you need parens there.
Oh, do I have one extra or?
No, but you have a bracket there at the start after points from XY. You see the, and I think you want parens because this is a function.
Okay. So this is.
Yeah, I see.
Oh, okay.
Yeah, there you go. Thank you. I think that'll do it, maybe. Oh, and then you need one more paren at the end to close off the geodata frame constructor.
All right. Let's check this.
Oh, wait. It
Yeah.
didn't like it, but also it did like it.
Yeah. I think the syntax is deprecated.
Yeah. I didn't get that though when I ran this cell. I got it earlier, like we saw, but I didn't get it this time. So I don't know what we did differently.
Maybe I do. I don't know if there is a way of defining that this should be longitude and this should be latitude. I think that might make
I
this
don't know.
easy. All right, so we have specified EPSGS4326. Now let's plot the data. Seems like they are loading the natural Earth loris, and then we are just doing America, so North America and South America. And we'll skip over rest of it because we're just taking a look at migratory patterns from almost North America to South America. So that says the head, and now we just need to plot them.
So it looks like we're going to need, 2 plots, right?
Yeah, so the first is just Americas, and then I need to, I guess, superimpose what we are building on top. So and I forget the initial one, how we were superimposing. So I'll just open one of our previous exercises and just go from there. So this is the first plot, and then we plot on top of that. So this is Ax equal to this, and then we plot which one is birds?
It's just birds.
Okay, there's just birds. So birds dot plot.
X equals X.
And x equal to x. And I don't know if we want marker size or not.
Yeah, I don't know what the default is. I guess we'll find out.
Yeah.
Oh, it's probably the same color. You may need to change the color.
Yeah. All right. So we'll go with this one, whatever we had earlier.
Sure. Makes sense.
And all right. So these are the different points that it has been marked on. So we can see a clear distinction that, all right, so these are, so we have some plots over here in North America, we have some plots in South America. There is some issue with it. I know that Central America is pretty warm even during winter, so you don't know the ones that are over here, if they're migrating to really South America or they are just migrating to these places. Because for them, when they're getting out of here, this is going to be pretty warm. I mean, that's where people come from here to Florida. So it's pretty similar to this. I mean, they can be coming over here. So I think that's what we are going to try to find next.